Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is Introduction to the Laplace Transform. Recall from your calculus that differentiation and integration are both transforms. That means they transform one function into another. So if you take the derivative of x squared, you will get 2x. And if you take the indefinite integral of x squared, you will get 1/3 x cubed. And remember that both of these transforms possess the linearity property. That a transform of a linear combination of functions is a linear combination of the transforms. This is what it was for derivatives, and this is what it is for integrals. In this section, we'll examine a special type of integral transform called the Laplace transform. In addition to possessing the linearity property, the Laplace transform has many other interesting properties that make it very useful in solving linear initial value problems. Let's look ahead and talk about what's going to be happening. So we'll have a blue differential equation that we're trying to solve. So this is the original problem, and that's the thing we're trying to solve, and what we're looking to do is think about solving it. But what happens is if we do the transform and we transform the original problem into the transformed problem and solve the transformed problem, then we can invert the transform to get the solution to the original problem. And the idea is that the green problem is easier to solve than the blue problem. And in many cases it will be because this will involve calculus over here. In the case of Laplace transforms, this will involve algebra. So let's do a few fundamental definitions then. If f of xy is a function of two variables, then a definite integral of f with respect to one of the variables leads to a function of the other variable. So for example, if I integrate this, I'll get 3y squared. So see it as a function of y. Similarly, a definite integral such as the integral from a to b of k, and this is a function of two variables now, s and t, f of t dt, transforms a function of f into of the variable t into a function capital F of the variable s. So we're particularly interested in an integral transform where the interval of integration is unbounded from 0 to infinity. If f of x or f of t is defined for t being bigger than 0, then this improper integral is defined as this limit. And you might remember that you take the limit as the upper limit goes to infinity of this expression. You studied that in your calculus. If the limit exists, we say the integral exists or is convergent. If the limit does not exist, the integral does not exist and is divergent. Often this means it is of infinite value. It blows up. The limit here will in general exist only for certain values of s. So moving on to a definition. The function k of st on the previous page is called the kernel of the transform. And if we choose k of st to be e to the minus st as the kernel, this gives us the Laplace transform. So here's the definition. So if f is a function defined for t greater than or equals 0, then the Laplace transform of lowercase f is equal to the improper integral from 0 to infinity e to the minus st times f of t dt, and this is said to be the Laplace transform of lowercase f, provided the interval converges. It's named in the honor of Laplace, and later Heaviside did a lot of work here, and we may talk more about him later. When the interval converges, the resulting answer is a function of s. So in general, we will use a lowercase letter to denote the function being transformed and the corresponding capital letter to denote its Laplace transform. So the Laplace transform of f of t is capital F of s. The Laplace transform of lowercase g of t is equal to capital G of s. And the Laplace transform of y of t, lowercase y of t, is going to be capital Y of s. And remember that the domain values of s of the Laplace transform depends on what the function being transformed is. So let's calculate an improper integral to remind us about that. So we say if c is a constant not equal to 0, you want to evaluate this integral. So you know what to do. Let's see how you did. Well, first of all, the integral from 0 to infinity of e to the ct dt is equal to the limit as n goes to infinity of 0 to n e to the ct dt. We have to use a change of variable here, so we're doing a use substitution. And so we will use the fundamental theorem of calculus to evaluate this before we do the limit. So, leaving the limit there for a moment, we calculate this, and we will get that this antiderivative is going to be 1 over c e to the ct, and I'm going to evaluate it at n and 0. So when I substitute those numbers in, I will get 1 over c e to the cn minus, and when I put 0 in there, e to the 0 is going to be 1, so that is 1 over c. I take the limit of this as n goes to infinity. Now, this is where you need to be a little bit careful, though, because if c is a positive number, then e to the positive number times n as n goes to infinity will blow up. It will become infinite. And so for this to converge, c must be less than 0. Now, if c is less than 0, then the limit as n goes to infinity of this is going to be e to the minus something, and that is going to go to 0, and so the answer will be minus 1 over c, provided that c was less than 0. Let's do another one. Compute the Laplace transform of 1. You know what to do. Let's see how you did. Well, this actually is, we put the function 1 there, but this is the integral we really computed before, except we had a c there instead of a minus s. So this is going to be minus 1 over a negative s, and this is provided that negative s is less than 0. Now, minus times a minus is a plus, and so we get that the Laplace transform of 1 is 1 over s, provided that if minus s is less than 0, s is bigger than 0. Notice the restriction on s. Like we've said a few times, this will often happen. Here's another problem. We're asking you to compute the Laplace transform of e to the at, where a is a constant. You know what to do. And we'll find out how you did when we turn to lecture 25.1.